This is your presenter, Asloob Mudassar, and I am presenting slide number 15A of the course on atomic and molecular physics. In the today's lecture, I shall be covering structure of helium atom, Pauli principle, angular momentum coupling, one electron system. And this is the first lecture of the category of many electron atoms. So this is the first lecture and the topic is many electron atoms. So many electron atoms. Structure of helium atom. Helium atom is the simplest atom of many electron atoms category. You know that if you consider many electron atoms category, then of course the helium atom is the simplest of all. It has two electrons and the ground state configuration is 1s2. The S shell corresponding to n is equal to 1 is completely filled. Possible excited states are electron 1 in a state n is equal to 1 with L is equal to 0. Electron 2 could be in a state with n greater than 1 and with the orbital quantum number has values L is equal to 0, 1, 2 and so on up to n minus 1. We have learned that the orbital quantum number ranges from 0 to n minus 1 in integer values. This is what we have learned before. So if one electron is in the state n is equal to 1, because we have two electrons in the helium atom 1s2, which means that if one electron is in state n is equal to 1, and you know that when we have s subshell it means L is equal to 0, then the other electron could be in a state which is greater than 1. So n could be 2, 3, 4 and any of these integer values, and of course the corresponding value of the orbital quantum number will be equal to 0, 1, 2, 3 and so on up to n minus 1. In one of the previous lectures, we dealt with the spectra of atoms with a single valence electron. Hydrogen atom, for example, has only single electron which is present in the hydrogen atom. So hydrogen atom is a very good example of a single electron atom in which the single electron is treated as the valence electron. We have also dealt with the alkali metal atoms. The outermost electron acts as a single valence electron. The remaining electrons are in closed shells around the nucleus, and their contribution to the total angular momentum L and the total angular momentum and the total spin angular momentum will be equal to 0. So capital L will be equal to 0. Similarly, capital S will also be equal to 0. That is, the total orbital angular momentum of the closed shell is 0. Similarly, the total spin angular momentum of the closed orbits will be 0. And their corresponding quantities, that is the orbital magnetic moment mu L, will be equal to 0. Similarly, spin magnetic moment mu S will also be equal to 0. This is what we have learned in the chapters on alkali metal atoms. And the outermost electron outside the closed shell of electrons will be treated as the valence electron. And the inner electrons, as we have said over here, for the inner electrons, the total value of capital L and the total value of mu L is equal to 0 for the electrons in the closed shells. Similarly, the total value of spin angular momentum capital S and the spin magnetic momentum mu S will also be equal to 0. Helium atom. For helium atom, there are two term systems: a singlet system and a triplet system associated respectively with the perihelium and orthohelium respectively. So you see that in the helium we have two types of heliums which are regarded as the perihelium system or the orthohelium system. For the perihelium system, the term symbols will be designated as a singlet system, whereas for the orthohelium, the system will be regarded as the triplet system. Singlet mean that the multiplicity of the system is 1, and the triplet mean that the multiplicity of the system is 3. So there are two main types of categories, that is we may encounter single terms with the multiplicity 1, or we may encounter triplet terms with the multiplicity equal to 3. This is what we shall learn in the rest of this lecture. In a singlet system, all terms are singlet, whereas in a triplet system, the terms are generally triplet in numbers. So when we talk about the triple system, it means that we have three terms. We have that is one term is split into three, and for the singlet case, one term is split into only a single. That is, there is no splitting for the singlet system. Whereas for the triplet system, there will be generally three levels corresponding to each of the level of the triplet system. While discussing the term scheme of the helium atom, we discussed two separate systems: singlet term system, triplet term system. Optical transitions following the rule delta L is equal to plus minus 1 are allowed within the singlet system and within the triplet system, but cross transitions between the two systems, that is from singlet to triplet and from the triplet to singlet system, are not allowed. That is, optical transitions between perihelium and orthohelium are not allowed. The two term systems and some allowed transitions are made side by side on the following pages. That is, we shall produce a diagram in which we shall represent the Grotrian diagram corresponding to the singlet system, and we shall also explain the Grotrian diagram of the triplet system. We shall produce these two diagrams side by side for comparison and quick reference in the following pages. For the perihelium, the two electrons which are in the 1s square may be regarded as 1s and 1s, and these are required to have anti-parallel spins, because 1s, when the two electrons are in the same subshell, it is required that their spins must be anti-parallel to each other, so that minimum configuration, that is the term in minimum configuration, can be obtained. So for the perihelium with the two electrons in 1s and 1s, we can say S1 is equal to half. That is, the spin quantum number is half. S2 spin quantum number for the second electron is also half, and the total spin of the system is equal to mod of S1 plus minus S2, where S1 and S2 are the spin quantum numbers. And you see that here I am putting their values, half minus half, that is equal to 0, because I am choosing the negative sign, which means that the two spins are anti-parallel to each other, and the total spin will be equal to 0. Now, as far as the orbital quantum numbers are concerned, for the 1s electron, I have L1 is equal to 0. For the second 1s electron, I have L2 is equal to 0. So capital L, that is the total orbital quantum number, will be equal to mod of L1 plus minus L2. And putting the values of 0 and 0 from both of these quantities, I have total value of capital L is equal to 0. And you know that when capital L, that is the total value of the orbital quantum number, is equal to 0, then the term associated with the capital L is equal to 0 is the S term. So S term, capital S term, is the spectroscopic terms associated with capital L is equal to 0. Now the multiplicity is given by 2s plus 1 is equal to 2, and from the capital S we are putting the value of 0 from here, which is shown in red, and then plus 1. So of course the multiplicity will be equal to 1, and the value of our total quantum number J of the atom will be equal to mod of L plus minus S. Since L is equal to 0, S is also equal to 0, so capital J is equal to 0, and the term can be designated by 1, which is the principal quantum number 1, and then we have 1s naught. There the superscript before the symbol S is actually the multiplicity. So here I have represented the multiplicity as the superscript before the symbol. This is the multiplicity, which is equal to 1, and capital S is the term symbol associated with L is equal to 0, and O naught as the subscript is the value of the total angular momentum of the atom or of the electrons. So you see that the term symbol 1 and 1s naught is actually the ground state for the perihelium atom, in which the two electrons are in the state 1s and 1s. So as the total spin capital S is equal to 0 for the perihelium system, the total spin angular momentum represented by the S vector is also equal to 0. And the total spin magnetic moment represented by mu S vector is also equal to 0. That is all the spin quantities are related, that is all the spin related quantities will be equal to 0. That is the total spin angular moment, total spin quantum number is 0, total spin angular momentum is 0, total spin magnetic moment mu s is also equal to 0. Ground state term for the perihelium is therefore 1 and 1s naught, or can simply be written as 1 1s, where the total quantum number j is equal to 0 is usually not written, because it is understood that when a value of capital J is not written, it means that the capital J value is equal to 0. Higher states for the perihelium atoms will be equal to 2 1s, 2 1p, 3 1s, 3 1p, 3 1d, and so on. And you see that these are the higher terms, higher perihelium terms. That is, this correspond, the first two terms correspond to principal quantum number n is equal to 2. Then the next three terms correspond to n is equal to 3. And then you see that I have written these as the multiplicity has been written equal to 1, which means that all the higher states in the perihelium atom are actually the singlet states. That is, these are the single states. Okay, each of these higher states are singlet state, as it has no fine structure. You know that in the fine structure, the orbital quantities will interact with the spin quantities. For example, orbital magnetic moment mu L will interact with the spin magnetic moment. Since S is equal to 0, the spin quantities are 0. So it means that there will be no LS coupling, or there will be no fine structure. And you know that we have learned in one of the previous lectures that in the fine structure there is a splitting of states because of the coupling of the orbital quantities with the spin quantities. Since our spin quantities are 0, so it means that there will be no coupling between the spin angular momentum and the orbital angular momentum. Similarly, there will be no interaction with the spin magnetic moment and the orbital magnetic moment. Due to that one, there will be no fine structure. And since there is no fine structure for the perihelium atoms, it means that all the systems will have only singlet states. So let me read the paragraph. Each of these higher states are singlet states, as it has no fine structure splitting, as it has no fine structure splitting, because for these states capital S is equal to 0, that is the spin magnetic moment, spin angular momentum, spin magnetic moment, or all these quantities related with the spin are equal to 0, and there is no L and S interaction. That is, the orbital angular momentum will not couple with the spin angular momentum. Similarly, their magnetic quantities, that is mu L and mu S, will also not interact with each other, and thus there will be no fine structure splitting. And since there is no fine structure splitting for the case of the perihelium atoms, being capital S is equal to 0, that's why we shall say that these states are the singlet states. Now let's talk about the orthohelium. In the orthohelium, one of the electron, since there were two electrons in the helium atom in the ground state as 1s2, so in the orthohelium system, one of the electron will be in 1s, the other electron will be in the upper state, for example, in the 2s state. So the lowest level for the orthohelium is 1s and 2s. And since the two electrons are now one of the electrons in 1s, the other electrons in the 2s, since they are sharing now different subshells, different s subshells, so they will have the spin parallel. So because they are not restricted in the same subshell, because now in this position they are in two different subshells, in two different S subshells. One is in one S, the other is in two S. So the two electrons can have parallel spins. So the first electron has a spin S, a spin quantum number S1 is equal to half. Second electron has a spin S2 is equal to 1 half, and the total spin is equal to S1 plus minus S2 mod. Now I am choosing the plus sign over here because I can have the two electrons to have the parallel spins. So so 1 half plus 1 half is equal to 1, and you know that I have shown that the two electrons have a parallel spin in this category. Now the orbital quantum numbers L1 is equal to 0 for S orbital. Similarly, for the 2s subshell, the value of L2 is also equal to 0. And the total L, that is the total orbital quantum number L, will be equal to mod of L1 plus minus L2, and that is the mod of 0 plus minus 0 is equal to 0. And you know that when capital L is equal to 0, the term associated with that one will have a symbol capital S. Now the multiplicity is given by 2s plus 1. So I am putting the value of capital S, which is equal to 1 as shown in the red, and the multiplicity becomes 3. That is, and now the J value is equal to mod of L plus minus S. Since L is equal to 0 in this case, so J will be equal to 1 over here. And the term designation will be 2 into 3s1, where 2 stands for the principal quantum number 2, 3 stands for the multiplicity of the system, S is the term symbol corresponding to capital L is equal to 0, and here 1 as a subscript is actually the total value of the quantum number. So we have 2 and 3s1 as the first or the minimum level of the triplet system, that is the minimum level of the orthohelium system. Thus, the term corresponding to first excited state for the orthohelium is 2,3s1 or simply 2,3s. Here you see that I have also omitted the total angular momentum J, but if you want to keep it, you can keep it over here. So you see that I have calculated over here the minimum value of the orthohelium system, which is 2 and 3s1. A total spin capital S is not equal to 0. The total spin angular momentum capital S vector will also be not equal to 0, and the total spin magnetic moment, which is usually the total spin magnetic moment is equal to the spin magnetic moment of the electron 1 plus the spin magnetic moment of the electron 2. This is a vector addition, and this is also not equal to 0. Because here for the case of the orthohelium system, capital S is not equal to 0, and the total spin total spin quantum number is not equal to 0, total spin angular momentum is not equal to 0, and also the total spin magnetic moment is not equal to 0 for the case of the orthohelium, as we have seen. That is for the state that we discussed 1s and the 2s state, we found that the capital value of that system will be equal to capital L is equal to 1. The resulting total spin, which we say that capital S as the spin magnetic angular momentum and mu S as the spin magnetic moment, have three possible orientations with respect to the internal magnetic field BL. You know that this is the internal magnetic BL, which we have already discussed in one of the lectures. So capital S and mu S will have three possible orientations with respect to the internal magnetic field BL of the system. And this BL is actually coupled to the orbital magnetic moment mu L of the electron. So you see that for the triplet system, capital S vector and mu S vector will have three orientations with respect to the internal magnetic field BL of the system. And this BL is actually coupled with the orbital magnetic moment mu L of the electron. This BL is what we have discussed in much greater detail in one of the lectures. The capital L and capital S, that is the orbital angular momentum and the spin angular momentum coupling. Resulting from this leads to a triplet fine structure splitting of the terms which have L not equal to 0. You know that here in the previous lecture when I discussed this example, then you see that I found that capital L is equal to 0 over here. And this is only possible when the two electrons are in the S subshell, that is in 1s and 2s. But now if the second electron is moved, for example, to the 2p subshell or the 3p subshell, and similarly to the D subshells, then of course the value of the capital L will not be equal to 0. Under that condition, then of course what will happen? Capital L, we can write that capital L will not be equal to 0. That is the orbital angular momentum will not be equal to 0. Under that condition, the triplet fine structure, there will be a triplet fine structure. You know that the fine structure means that the coupling between the orbital angular momentum and the spin magnetic moment, or the interaction between their magnetic moments, that is the orbital magnetic moment mu L and the spin magnetic moment mu S. Then the coupling, because then due to the coupling between these two magnetic momenta, then of course the fine structure is produced, or the fine structure appears. And then of course in this particular case we shall see that there will be a triplet fine structure, because the multiplicity for the orthohelium system will be equal to 3, as we have seen, because the two electrons will be in a parallel spin configuration. Optical transitions between a singlet and a triplet system are forbidden. That is, change of spin from anti-parallel to parallel and vice versa is not allowed. That is, there will be no transition, optical transition between the triplet system to the singlet system, and from the singlet system to the triplet system. These are the forbidden transitions. Energy difference between the corresponding singlet and triplet terms is called symmetry energy. That is, for example, if you consider two energy terms, one from the singlet system and the corresponding energy term from the triplet system, then of course there will be an energy gap between the two states from the two different systems. Such an energy difference is called symmetry energy. It arises from the difference in the average distance between two electrons, one with symmetrical wave function while the other with anti-symmetric wave function. So you see that the two electrons for the orthohelium system will be at two different average distances from the nucleus, and one will have the symmetrical wave function, whereas the other electron will have the anti-symmetric wave functions. These are the empirical rules that I have mentioned over here by analyzing, but the complete analysis is given by the quantum mechanical treatment. Since I cannot produce the quantum mechanical treatment for all these concepts, so I have borrowed some empirical rules from them, and some of the empirical rules are what I have given over here, followed from the quantum mechanical description of the treatment, or from the optical spectra we have obtained, that is from the experimental spectra. Term diagrams for the singlet and triplet systems for the helium atom are shown side by side on the next page. For example, this is what you can see. Singlet system on the left hand side and the triplet system on the right hand side have been shown. You see that this level, that is the top level, is the ionization energy of the electron, because after that there are no levels. So the top upper level black line or black horizontal line will represent the ionization for the singlet system and for the triplet system. Now look at the energy range. Energy starts from the zero, because at zero energy the system is ionized, and then you see that the binding energy is increasing downward from -1 electron, -2 electron, and so on. So you see that up to the -5 electron, I have shown the scale, which is not the linear scale, but I have adopted this scale in such a way that most of the energy spacing can be represented very easily. But you know that the lowest level of the orthohelium system, that is the triplet system, is 2 3s1 state. This is the lowest level, and this lies at an energy level of the order of -5 electron volt. Whereas the lowest level of the singlet system, you will see it has an energy of the order of -24.47 electron volt. So from a -5 to -25, the scale is actually completely non-linear. But the scale upward from -5 to 0 volt is roughly you can say that is roughly linear. But it is completely non-linear from -5 electron volt from the 25 electron volt. So the lowest level or the lowest energy term for the triplet state lies at an energy level of -24.47 electron volt, and the energy term is 1s, which you may call as the ground state of the singlet system. And the lowest state of the triplet system is a 2 3s1, which is actually at a energy gap, at an energy of minus electron volt, at a binding energy of -5 electron volt. You see that here I have given delta L is equal to +-1 as the optical transition rule for both the singlet system and for the triplet system. That is, for all transition within the singlet system, you have to follow delta L is equal to +-1. Similarly, for all the allowed optical transitions for the triplet system, the optical selection rule will be equal to delta L is equal to +-1. The transitions that will take place in the singlet system will give you the wavelength in the order of the spectral lines will be in the range of UV, whereas for the triplet system, since there is a narrow energy gap between them, the spectral lines will be invisible or will be in the IR, infrared. And you see that I have also shown some energy gap between them. For example, the second level of the second highest level of the singlet system is 2 1s0, whereas the lowest level of the triplet system is 2 3s1. And you see that here I have shown the energy gap between the two levels, which is equal to 0.8 electron volt, is also known as the symmetry energy. Now look at the second higher states. For example, 2 1p is the next higher states for the singlet system, whereas 2 3p012, which are actually the triplet states. This singlet state, which is being shown in green, is actually these triplet levels, which are very close to each other, and I have shown only one level for them. And you know that there is also an energy gap between these two relevant energy states of the order of 0.25 electron volt. And of course, when you go to even higher states, then of course this difference of energy, that is a symmetry energy difference between the relevant energy states in the singlet and the triplet levels, will decrease. So S0 is the total spin for the singlet system. S1 is actually the total spin for the triplet system. And you know that when capital S is equal to 1, then of course the multiplicity will be equal to 3. And when capital S is equal to 0, the multiplicity will be equal to 1. That's why we have the singlet system and the triplet system. And you know that here I have also shown some transitions over here. Let's discuss the transitions which are being followed by the selection rule delta L is equal to +-1. These transitions are shown, and you can see that these transitions obey delta L is equal to +-1, and these transitions are shown. You can find these one to be correct, and you can also understand these one by yourself. For example, from 2 1p, from this green, we have the transitions to the red lines, which are 1D lines, and again to the 1s lines, which are shown in dark brown. So similarly, I have also shown the states transition between the states of the triplet system, that is 3s1 to the transitions from all states in green have been shown. Similarly, from green, you can show the transition up to the D states, and from the P state, you can have the transition up to the S states, where delta L varies by +-1. So I have shown some of these states over here. But you know that I have not shown any state, any transition between the triplet system and the singlet system, because the transition between triplet system and the singlet system, that is the transition from triplet to singlet and from the singlet to triplet, are forbidden. So all the transitions within the triplet will take place following the selection rule delta L is equal to plus minus 1. Similarly, all the transitions within the singlet system will take place following the selection rule delta L is equal to plus minus 1. So you see that the triplet system expands up to an energy difference up to a minus 5 electron volt, whereas the singlet system is more strongly bound by the nucleus, and you know that the lowest level goes up to minus 24.47 electron volt. So I hope that this is quite clear, because I have discussed many Grotrian diagram in many of the previous lectures. So I think that if you have followed those, it is very obviously very clear, and you can understand the singlet system and the triplet system for the helium atoms very easily. But remember that each line in the triplet system will be actually a triplet system. So this is the Grotrian diagram of the helium atom. The second lowest state of the singlet system is 2,1s, and the first lowest state of the triplet system is 2,3s. Both of these states are metastable states, lifetime longer compared to 10 to the power minus 8 seconds. So 2,3s1 and 2,1s0, these are the metastable states. That is, their decay to the ground states is not possible under normal conditions. Singlet system expands over 25 electron volt, whereas the triplet system spans only over 5 electron volt. Now you see that I am going to write down the energy equation for this helium system. The total binding energy of the helium atom can be written as E is equal to minus Ze square over 4 pi epsilon naught R1. This is the binding energy of the electron 1 in the helium system. And then minus Ze square over 4 pi epsilon naught into R2. This is the binding energy of the second electron in the helium atom, whereas R1 is the distance of the first electron from the nucleus, and R2 is the radius of the second electron from the nucleus. And then we have the repulsive energy between electron 1 and 2, which is given as E square over 4 pi epsilon naught R12, where R12 is the distance between the electron 1 and electron 2. So you see that this is the total binding energy of the helium electrons that I have written and shown in equation number 15.1. So I can write them as E is equal to binding energy of electron 1 plus binding energy of electron 2 plus repulsive energy between electrons 1 and 2. And you know that here R1 is the distance of electron 1 from nucleus, R2 is the distance of electron 2 from the nucleus, R12 is the distance between electron 1 and 2. The repulsive energy term depends on two quantum numbers, principal quantum number n and the orbital quantum number L. So the repulsive energy term depends on NL and N and L states. So N and L states the electrons occupy, because the spatial distribution of the electron depends on the two quantum numbers N and L. Since the spatial distribution of these electrons in the helium atom depends on two quantum numbers n and L, principal quantum number, the orbital quantum number, that's why their repulsive energy will also depend on these two quantum numbers. The repulsion energy thus lifts the L degeneracy to a considerable degree. That is the energy due to the repulsive force, due to the repulsive energy term will depend upon two quantum numbers n and L. That's why we can say that the L degeneracy is lifted. You know that the first term, or the binding energy of electron 1, the second term or the binding energy of electron 2. These two depends only on the principal quantum number n, whereas the repulsive energy term depends on two quantum numbers n and l. That's why we can say that on the left hand side the energy capital E actually depends on two quantum numbers n and l. So we can say that the L degeneracy is lifted. That is, now the energy is going to depend on the orbital quantum number L also. Schrodinger equation cannot be solved for equation 15.1 in the independent particle model because of the presence of this term, that is the third term, that is the repulsive energy term between electrons 1 and 2. Because of the presence of this one, it is difficult to solve the Schrodinger equation in the presence of equation number in the third term in equation number 1. In the independent particle model, where each electron will behave independently in the helium atom, the third term is neglected. The helium atom energy becomes equal to the sum of the energies of the two hydrogen atoms. So under that condition, the equation 15.1 in terms of the Rydberg constant R and neglecting the third term can be written as capital E is equal to minus R into H into C into Z square over N square for particle 1. Similarly, subtracted from it the second term, which is a minus R into H into C multiplied by Z square over N square, and this is for the second electron. And this energy term is shown in equation number 2. This is the energy term in which we have considered that the two particles are behaving independently, and the helium atom energy under that condition will be acting as if the energy of the two hydrogen atoms have been combined together. Expected ground state energy. You know that in the ground state energy, we also refer to as the ionization energy, because the energy that is required to ionize an electron from the ground state will be referred to as the ionization energy of the helium atom. Now, if we calculate the ionization energy of the helium atom using the theoretical model, we can say that the ionization of the helium atom will be equal to 2 times minus 54.4 electron volt is equal to minus 108.8 electron volt. This is the theoretical value. And you know that in the theoretical value we have the ionization energy for one of the electrons, and then we have multiplied by it to get the total ionization energy of the helium atom, which is equal to minus 108.8 electron volt. This is the theoretical value. Now the work done for the removal of the single electron from the helium atom will be equal to 24.6 electron volt, and the work done for the removal of the second electron from the helium atom will be equal to 54.4 electron volt. Now the total work done required to remove the two electrons from the helium atom will be equal to 79 electron volt. And this is for the production, that is, you want to produce doubly ionized helium. So the energy required to remove the two electrons or to produce a doubly ionized helium atom will be equal to 79 electron volt, and this is the experimental value. So you can compare the difference between the theoretical value and the experimental value. A much greater difference between the two. Because you see that for the theoretical value we have calculated that the energy required to remove one of the electron is minus 54.4 electron, and we have multiplied it with the 2 because of the factor that two electrons are present, and then we have calculated the theoretical value. But of course the experimental value is the real value, and you can see the difference between the two values, that is the difference between the theoretical value and the experimental value. Ionization energy for the hydrogen singly ionized atom is 13.6 electron volt. Ionization energy for the helium singly ionized atom is equal to 13.6 times Z square electron volt. That is, if you want to calculate the ionization energy of the helium atom using the ionization energy of the hydrogen atom, then you need to use this formula, which is equal to 13.6 times z square into z square electron volt. And for the helium atom, z, the value of z is equal to 2 and its square is 4. So multiplying together, you get 54.4 electron volt, which is the expected value. And you can compare that this expected value for the helium singly ionized atom calculated using the ionization of the energy of the hydrogen atom is equal to the energy required to remove the second electron from the helium atom, which is also 54.4 electron volt. Experimentally found value for the helium singly ionized atom is 24.6 electron volt, much lower. So why this energy is much lower? So you see that if you remove single electron from the helium atom, you need 54.4 electron volt. But experimentally we have seen that this energy is actually 24.6 electron volt, much lower than this. This is the expected value. Using the formula of hydrogen, using the ionization energy of hydrogen atom, and using this formula, which is 13.6 times z square electron volt. So this value, which is the experimental value, is much lower than 24.6 electron volt, is much lower than 54.4 electron volt. To remove this discrepancy, it is important to take into account the interaction energy between the two electrons. So you see that in the ionization energy that we have calculated the expected theoretical value, we have not taken into account the interaction energy between the two electrons. That's why the difference is there. Ground state of the helium belongs to the lowest singlet state that is 1s state, and not the 1,3s state, which is the lowest triplet state. The later one has much higher energy, that is this one. In the 1s, that is in the lowest singlet state, the two electrons have antiparallel spins with ms value not equal to ms2. That is, the spin magnetic quantum number of electron 1 is not equal to the spin magnetic quantum number of electron 2. That is the two different sets of quantum numbers, n1 l1 ms1 and n1 l1 ms2. Whereas in 1,3s, the two electrons have parallel spins. That is, the value of their spin magnetic quantum number are also equal. That is, for the 1,3s, that is for the lowest triplet state, the two electrons have the same set of quantum numbers, n2 l2 ms2 or n2 l2 ms. So ms, you see that is the same. So that is why the two set of quantum numbers are also same for this state, for this triplet state. Starting point for the Pauli principle, reported in the year 1925. The electronic states of an atom can only be occupied in such a way that no two electrons have exactly the same set of quantum numbers. So you see that if the electrons are in the same subshell as in the case of opposite spins, then of course the two electrons will have opposite spins if they want to be located in the same subshell. But if the two electrons are being occupied in different subshells, then of course the electron will have parallel spins. That is, in that case, their set of quantum numbers will be equal to each other. But if you want to accommodate the two electrons in the same subshell, then of course their quantum numbers will be, their set of quantum numbers will be different. That is for the case of 1s 1s. The two electrons are in the same subshell and they must have anti-parallel spins, and their set of quantum numbers will also be different from each other. But if they are in the other state, that is the one electron is 1s, the other electron is 2s, they are in two different subshells, then of course the electrons will have parallel spins and the two set of quantum numbers may be equal. So this is what I have explained the Pauli principle for the two electrons with the anti-parallel spin and for the two electrons with parallel spins under the condition when the two electrons are in the same subshell, they must have anti-parallel spins. And when they are in different substates, then they will have then they will have same quantum numbers, and of course the spin will also be the same for the two electrons. Empirical rules stated earlier. There is always a unique ground state which has the lowest principal quantum number n. So you see that for the ground state, the one basic need is that, or one basic requirement is that the ground state is the state with the lowest value of the principal quantum number n. It has the lowest multiplicity. So the second criteria is that the multiplicity should also be lower for the ground state, and the multiplicity capital M is given by 2s plus 1. That is the lowest value of the total spin quantum number, and you know that this capital S is actually the total spin quantum number, so multiplicity will be lower when the total spin quantum number S is also lower, which is compatible with the lowest set of quantum numbers. So the quantum numbers must have a lower set for the ground state. Now angular momentum coupling. One electron system. Individual angular momenta for example, for a single electron represented by L vector and the S vector. L vector is the orbital angular momentum of the single electron, and capital and S vector is actually the spin angular momentum of the single electron. These individual momenta combine to give a resultant angular momentum J. For the single electron, we can represent J in a small alphabets. So this could be J dot, and this is the total angular momentum of the electron, which results when this orbital angular momentum and the spin angular momentum combine together. Empirical spectral analysis gives one rule: the total angular momentum of the filled shells is equal to 0. So if you have filled orbits, for example, in case of alkali metal atoms, there is only one valence electron outside the closed shell of electron, and for those closed shells, the total value of the quantum number capital J will be equal to 0. Ground state of all noble gas atoms, because you know that all ground state noble atoms have completely filled orbitals. So for the ground state of all noble atoms, for example, xenon, argon, krypton, xenon, the ground state configuration is 1 and 1s naught. That is the total spin, that is the total angular momentum capital J of the atom is 0, which is written as a subscript with 1s naught. For the calculation of the total angular momentum of an atom, only angular momenta of the valence electron is considered, because the closed shell orbits have 0 contribution towards the total angular momentum of the atom of the electron. These angular momenta are coupled by means of magnetic and electric interactions between the electrons in the same atom. And this is what we have discussed in much greater detail, how the magnetic and spin interactions are responsible for the coupling of the angular momenta in some of the previous lectures. There are specific quantum mechanical rules which help to produce total angular momentum capital J of an atom. Vector model provides insight into the composition of individual angular momenta and their resultant in the absence as well as in the presence of the magnetic field. The two initial cases for the angular momenta coupling will be discussed later. For example, the LS coupling or the Russell-Saunders coupling and the JJ coupling will be discussed in the next lecture. So this lecture is continued, and you know that this lecture falls in the category of many electron atoms. So this is the today I presented the first lecture of the many electron atoms, and this lecture is continued. In the next lecture I shall be presenting the second lecture of this series, in which I shall explain the LS coupling and the JJ coupling. So this is the end of slide number 15A of the course on atomic and molecular physics.